Good afternoon. I've decided in this lecture to take a little detour. We started last time in perturbation theory. I've tried to explain the general logic of perturbation theory, which is to add an epsilon to part of the equation and then solve for the function in powers of epsilon. Now, in this, I wanted to give a few examples, but the main part of this lecture is supposed to be the application of perturbation theory to quantum mechanics, which is a little bit trickier than the standard applications of perturbation theory, and it's a big calculation. So it will take us a substantial amount of time, and my nightmare is to get stuck in the middle and have to continue it in the next week, which I don't like this to happen. So I've decided to start with, although it will be nicer to do more examples, I put these examples aside for the moment. I will return to them. And I'm starting with the application of perturbation theory to the Schrödinger equation, which is a classical, when I ended up my first degree, I was sure that perturbation theory is a branch of quantum mechanics. And it took me a lot of time to realize that perturbation theory is the most important thing in physics. So, so today I would like to start with the calculation with the application of perturbation theory to quantum physics, and then, if time will allow, I will go back to the other examples that I wanted to address that are much more simple, and if it will not allow, I will go back to these examples in the next lecture. Okay. So, and while doing perturbation theory for Schrödinger equation, I will again try to make a distinction between the abstract theory and the concrete example. Right? So I will my attempt here is to run in parallel something about something abstract and something more specific. Okay? So let's start with the definition of the problem. So what is Schrödinger equation? For us, Schrödinger equation is minus y double prime plus v of x y equals e y. Y is of course the psi from quantum physics. All the constants were taken to be 1, h bar is 1, m is 1, 1/2 is 1, right? And you get something like that. Okay? With the boundary condition, y at plus minus infinity is 0. Okay? And to be concrete, okay, this is no. I don't have.
Wait, why do you assume it's 0? If it's a free particle, it's not a.
Free particle is not a legal. It's not, the solution you're writing for free particle e to the ikx is not in Hilbert space because it's not L2. If you take the absolute value and integrate over all space, you get infinity, right? So I mean, the proof that that 1 equals 0. No. Okay. So here is the proof. So I'm taking, that the p of and x, the commutation relation of p of x and x is I. I hope that it's not minus I, but something up to, right? Mm-hmm. You agree with me?
I h1?
No, h1 is equal to
h1.
Okay.
Okay.
1 is equal to
And now, let's take, so it is still true that, right? You agree with me? Mm-hmm. Right? Because this is the expectation value of a constant. Okay? And now let's take psi to be a specific something which is an eigenfunction of P. What's an eigenfunction of P? It's P psi equals, let's say, K psi, well, so psi is e to the I kx I, h bar, something like that, right? So eigenfunction, so I'm taking, let's call it psi p. Psi p is the eigenfunction of the operator p. And here I will write px minus xp. That's legal, right? Because this is just a commutation relationship, right? And now I am writing psi p here and close the bracket. Now what this gives me, this is I. Okay? On the other hand, now I have the right to operate with this p on this and with this p on that, right? Because p is an Hermitian operator. And what I will get is eigenvalue. So when p is acting on this, it gives me small p. It's the expectation value, right? So what I will get is p. So I'm saying that p psi of p is p tilde psi of p, right? So I get p tilde, okay, times what? Times p psi p, sorry, psi p. And here I have x minus x psi p, which is 0. Okay?
So you prove that
So I prove that I equals 0 and multiply this by I, and you get, by minus I, you get minus 1 equals 0.
Minus.
No, by minus I.
So,
I
Multiply
don't
the-
think it
Okay.
is mathematically correct.
No, 0 is not 1. I mean, the statement that 1 equals 0 is not mathematically correct.
But what you did here is mathematically correct.
Apparently no. Yes, so what I did here is to use your belief that psi p is a legal wave function. It's not. Right? And if you try to do that with something like eigenfunction of p on a circle, you will find out what's the mistake. But I mean, this is just a comment saying that your happiness with eigenfunctions of p is not okay. Sorry. Okay, so this is a Schrödinger equation, and I do ask psi at infinity to go. Okay, and now the case in which we would like to implement perturbation theory is when we have psi double prime plus v of x y plus w of x y equals e y, such that, okay, so I splitted this v into v and w, such that I know how to solve it without the w, but I don't know how to solve it with the w. Okay, to be specific, let us assume that we take the Schrödinger equation y double prime plus x squared over 4y equals e y. Y at plus minus infinity is 0. What is this equation? Harmonic oscillator. And you all know that if I'm asking what is the ground state of this problem, the answer is in this fantastic units where everything is 1. The answer is y is equal to e to the minus x squared over 4. Now let's plug it here, just to make sure. Right? Let's go and okay. Let's plug it here. So I have, so that's right. Y prime is what? Is minus x over 2 e to the minus x squared over 4. Right? And y double prime will be minus 1/2 e to the minus x squared over 4 plus x squared over 4 e to the minus x squared over 4, depending if I'm taking the derivative here or here. You agree? Okay? And when plugging it here, I will get minus y double prime, so it will be 1/2 y plus x squared over 4y. This will be the minus y prime. Sorry, minus x squared over 4y. And now I have plus x squared over 4y equals ey. You see? Which implies that this cancels out, and it implies that e is 1/2. So the solution, here is the solution. This is y, and e is 1/2 for this one. Any problems? Now, I mean, if you have any problems, please let me know, because this is supposed to be the simplest part of the calculation. Okay, so I know how to solve the Schrödinger equation for harmonic oscillator and to find the eigenfunction and the ground state eigenvalue. Okay, now the question is how to solve the anharmonic. Okay, so let's write now a new equation. Plus x squared over 4y plus x to the fourth power over 4y equals ey. You see? This is the Schrödinger equation for anharmonic oscillator. You see why it's anharmonic? Right? It implies that if v of x is x squared over 4 plus x to the fourth power over 4, right? Then f, the force in the corresponding classical Newtonian equation, is minus dv dou x, as you remember from the first year, and this is minus 1/2 x. So this is Hooke's law. You get a force that takes you back to 0 when the force is proportional to the displacement, right? But then you have now another term which is minus x cubed. Why? So this implies that when you push it too much for small x's, this is still the solution, right? I mean, because you can neglect x cubed with respect to x. But if you have large displacement, then you have extra force. You see, extra force that is not harmonic anymore. I mean, usually, you always have such anharmonic deviations. By the way, they shouldn't be all positive. It may be negative. I mean, because if you have plasticity, then then you have less response than less sublinear response at long distances, because you have plastic deformation of the spring. But for the moment, you see, this is a very important problem, and this is a corresponding Schrödinger equation, again up to rescaling of all of the constants. This is the mathematical essence of the corresponding Schrödinger equation, and nobody knows how to solve it. Nobody knows how to solve it. There is no solution for this equation. Okay? And suppose that for whatever reason on Earth, you want to know what is the lowest eigenvalue of this Schrödinger, of this potential. You know that when if this term was not here, the lowest eigenvalue was 1/2, and the lowest eigenfunction was this exponent, the Gaussian. But the question is, what's happened when you have this term? And the answer is, nobody knows. The only route for which this problem is accessible for us is to add our beloved epsilon here,
and assume that epsilon is small enough.
No.
You want it to be wrong.
And calculate the perturbative expansion order by order in epsilon, and then sum all the terms in the series, and then plug epsilon equals 1. Oh, okay, you can do that whatever order you like.
But you can have infinite amount of order for epsilon. What are
Yes, yes, definitely.
So
Okay, wait, that's,
זה מה שעשינו כל
but okay, for the moment, for the next 20 minutes of the lecture, let's assume that epsilon is actually small, so that the perturbation is indeed small, and we are interested in the lowest order or the next lowest order perturbation. You see, and this is not the case, but let's for the moment assume that this is the case, that epsilon is indeed small. This shouldn't be the case, but let's assume. Fine. So the question is now what we supposed to do in such a situation, and what we have suggested in the last lecture is to attack this problem perturbatively. What does it mean? It means that we will assume that y is the sum from n equals 0 to infinity of yn of x times epsilon to the power of n. Okay? And then we will plug it here and collect terms that are in order to each order of epsilon. And we know that we should put the boundary conditions 0 in the y naught. Here it's not a point because we put this boundary condition for every y. Each of these y will satisfy the same boundary condition in this specific case. If we have something non-trivial here, then we will put it at y naught, and all the others will satisfy this boundary condition. And we would like to plug it here and to get results that will be correct order by order in epsilon. What we know, what we already know, we already know what is the first term in this. Right? This is the advantage. You should always start in a place where you know the first term in the perturbative expansion. Otherwise you did nothing, right? You take an unsolvable problem and map it into another unsolvable problem. So we must start with y naught that we know. For example here, this is y naught, this is y naught tab, and this is y naught double prime. So, okay? Are you with me? Good. However, in the application to the Schrödinger equation, we have a problem that we did not face yet. And the problem is, in most cases we do not face, but here we face it. The problem is that the constants of this equation, not all of them are independent of epsilon. Right? Because we have here E. And we want the E to be epsilon dependent also. Right? So we must admit that not only Y is such a series, but also E is a sum from n equals 0 to infinity of epsilon to the power of n En, where E0 in this example is 1/2. Okay? And you understand that here it's completely general, so you may take V to be the hydrogen atom, and W will be the magnetic field, and so on, right? But this is a concrete example of that allows us to show the mathematical problem without getting involved into, the physics. I mean, this is a very simple mathematical problem. Good. So, okay, so let's continue. What is the next step? The next step, we have to plug these two expressions into the Schrödinger equation and calculate things order by order. Okay? So let's switch code. White box. Okay. Let's start here. What's the zeroth order of the calculation?
The zeroth order of the calculation will be the
I'm plugging this and this into that.
The zeroth order of the calculation will be the
Sorry,
solution.
I'm plugging them into this, right here.
The zeroth order of the calculation will be the solution without the perturbation.
Yes. So the zeroth order will be minus y naught double prime plus v of x y is equal to e naught y. Are you with me? Good. This is simple because we assume. Okay, now, what will be the first order? So this is the equation, epsilon to the power of 0. Good. This is y naught and this is y naught, and we know everything. We know that y naught, for example, in this equation, is the harmonic oscillator. This is y naught, this is in. Okay, next. What will be the story when I have epsilon to the first order in epsilon?
minus y1 double prime
Minus y1 double prime plus
v of x
v of x
y1
y1, good.
plus epsilon
No, the epsilon is already outside.
plus w of x y naught.
Plus w of x y naught, you see what?
Yes.
Yes,
Equals
is equal to
E1.
E1, Y1.
Actually, it will be sum. E0, Y1.
good,
E1,
very good. You see?
Y0.
Because if I'm writing E naught plus epsilon E1 times Y naught plus epsilon Y1, then I have two terms to keep that are first order in epsilon. One of them is, right, is so I have here E naught Y1 plus Y naught E1. You see? Good. This is the first order, the first correction, right? Remember that, for example, if I will take it if I'm speaking about the coefficient of E square, just from here, right, what I will get?
Will be
I should write E naught plus epsilon E1 plus epsilon squared E2 times Y naught plus epsilon Y1 plus epsilon squared Y2, right? And to collect all the coefficient of epsilon. Okay, let's do that. What's happened to the second order? Right? How the equation looks like?
minus 1
Minus y2 double prime
plus
plus v of x times
y2
y2 plus
w of x
w of x times
y1
y1 that I discovered, I know what it is from the last step, is equal to
E0 y2
E0 y2
plus 2
plus
2e1
2e1
y1
y1 y2.
not 2
I have e1 y1. There is no two, not two of them,
not 2
right? Only one of them plus
E2 y
e2 y0. You see? And this is how it goes further and further. Okay, so now we have essentially discovered what is a general term in the perturbative expansion. Good. Now that's nice. We have to solve it. So let's look at the first order correction to understand what kind of problem we have. And I would like to isolate. Okay, so I know everything with naught, with zero, I know. And I don't know everything that is not zero. Right? So I can write it now as, right? I can write it now as minus y1 double prime plus v of x y1 is equal to that minus w of x y naught. Right? If this was the equation, then I have an inhomogeneous second order equation for y1. Right? Because here this is known. For example, here this will be x to the 4 over 4 times e to the minus x squared over 4. Right? You see? So this is a function, something that depends on x, and I know essentially. So this is just an inhomogeneous differential equation. However, I have another two terms, which are plus, the E0, Y1 also goes here. So here I have minus E0, Y1, yes, is equal to minus W of x, Y0, minus plus E0, Y, E1, Y0. Okay. So suppose I have a friend who knows how to solve any second order differential equation, homogeneous or inhomogeneous. Okay, this may be a very difficult equation, but let's forget about the difficulty and suppose we have a machine, we have a friend, we have I don't know whom, we have a mathematician who knows what? Yeah, who knows how to solve every differential equation, every inhomogeneous second order differential equation at 0 time. Am I happy? Can I see that and call my friend and tell him, okay, you are a mathematician, here is an equation, please give me the answer? No. Okay? The reason why I'm asking, because even if we have such a fantastic friend, if you find such a friend, let me know. Even if we have such a fantastic friend, he or she will not help us. Why? Because first of all, because we don't know what E1 is. We have a parameter.
That the parameter is the thing that we want to find.
Okay,
What we know to
and
find.
even worse, how one solves second order differential equation? Okay, I gave my example was not, my friend, I have a friend who knows by heart all the common techniques, right? Not a magic friend.
You use the Frobenius, you use all Frobenius sum,
Okay.
or regular sum, or any other
The
sum.
standard way to solve, I mean, this is the solution for this. If you have the homogeneous part of this inhomogeneous equation is what? Is the same. Is a zero order Schrodinger equation. So I know what is the homogeneous solution. And when I have an homogeneous solution, what should I do? Variation of parameters, fantastic. So
But the problem
apparently,
is that the parameter is unknown.
what?
But your problem is that your parameter is unknown.
Okay, suppose I know what E1 is. Suppose somebody told me what is E1. Then what I expected to do, I will take this, I will take the solution of the zeroth order and do variation of parameters. This is not going to work. Why? Because the solution we have specified here is only one of two solutions. There is another solution. And the other solution will give us, is diverging at infinity. I mean, this is why we are not using it. Right? There is a solution. It's not in Hilbert space. Okay? So it's not L2. So we cannot do variation of parameters to address this equation. Instead, but we can do something. What we can do is a trick known as reduction of order. I don't know if the teaching assistant told you about that, but essentially, if you have a differential operator, let's say second order equation, like second derivative plus whatever, working on y equals 0, right? And it has two solutions because this differential operator has a second derivative. It's a second order differential equation. If you know one solution, if you happen to know one solution, then you can write u. So let's assume that you know one solution, y not. Then you can write L. You can define a new, what I would like to say. Yes, you can define y1 as u times y naught, and the equation you will get for u is the first order.
Oh, it was in the homework.
It was in
Such a
homework.
task.
Yes. Okay. So this is what we are doing.
Yeah.
So what we are doing now, we would like to define the solution for this equation, right? As u or something, maybe I will call it a different name, but times y naught, where y naught is the solution of the is the known solution of the homogeneous part. Right? This is a trick. And then we are going to get a first order equation in a first order inhomogeneous linear equation. So we are taking this, okay, and we plug. So our assumption is that
Wait, and what is u?
y1 is
We need to find.
yes, y1 is y naught times f1. f1 is a function of x.
Is a function of what?
Of x.
Oh.
Is a function of x. Good. Then what will be? Okay, let's plug it here. Right? We have to plug it into this equation. What we are going to get? Mx. Okay, let's start. Minus, I have to take the double prime of y1. So it will be y naught double prime f plus minus 2 y naught prime f prime. This is f1 prime. Minus y naught f1 double prime. You agree? This is the first term. And now we have plus v of x times y naught times f1 minus e naught y naught f1 is equal to minus w of x y naught without f1, you see, plus e1 times y naught. Good. Okay, now let's see how this trick.
You can get out f1 as the common
No, here I have f1 prime and f1 double prime.
and everything what with f1 is cancelled because f1 because the homogeneous part is equal to 0.
I'm not sure that we are speaking about the same thing, but I would like to
No.
note, okay, notice that
No.
this term plus this term plus this term is simply f1 times that.
No, this is what I said.
Okay.
This is what I mean.
So the
We've seen
three,
it in the homework.
what?
We've seen it in the homework.
Ah,
עשינו את זה ל-no DE.
okay,
He gave us some way how to
good.
extend second
So
order to third order.
these three terms go away. Thanks God.
Second order.
So we get
And what we have gotten?
Do it.
got the first
Ah,
order.
and now I can.
Left with
Okay.
equation of x.
Wait.
Wait, is f1 e0
Okay.
or e1?
Now I can.
Wait, you have on the other side f1?
Yes, this is the equation. This is the equation I've gotten, which is, let's write it. It will be minus 2y prime f prime minus y0 f double prime is equal to minus w of x y naught plus
E1.
E, you wrote f in
what?
It's E1.
It's e1, not f1.
Ah, e1. So
I don't know why you have
plus e1 y naught. Okay? Good. This is a equation, okay, where f is f1, sorry, I forgot the index 1, and f goes to infinity at plus 1 is infinity, exactly like y. Okay. Well, I'm not sure. F only, I mean, because y naught, the solution is y naught of a times f1. So our only constraint on f1 that it will not go to infinity faster than Gaussian. Right? Because we want this to go to 0 in infinity, so f1 maybe whatever we like. Any function that converges at infinity faster than a Gaussian. Good. Okay. So this is the equation, and now this is the equation for the first order, right? Now look at the second order. I will use the same trick, except that I will write y2 will be y0 times f2. Right? Because here also I can take the for the second order. Okay, let's do this. Let's do this. For the second order, okay, I'm writing minus y2 double prime plus v of x y2 minus e0 y2. This is the homogeneous part, which is exactly the equation for y2 for y naught. So this is solved by y naught, and this is equal now to minus w of x y1 plus e1 y1 that I've already solved, right? Plus e2 y0. Yes? And again, if I'm writing y2 as y0 times f2, what I will get is, I will plug it in the same tricks, right? So I will get minus 2 y naught f2 prime minus y naught f2 double prime. It's just replacing, I mean, in the left hand side, it is just replacing
y2, it's y naught prime.
Yes, y naught. It's exactly the same, just replace the 1 by 2. On the right hand side, I will have minus w of x f1 instead of, sorry, y1. So it's y naught f1, right? And plus e1 y naught f1 plus e2 y naught, and so on and so forth. Okay? You see what I'm doing? Good. Now the question is how to solve such an equation.
Wait, but the homogeneous solution to both f1 and f2 should be the same homogeneous solution because it is the same equation.
No, the y naught is the same y naught. I can write here. I've written that way. You see, and this part is exactly the homogeneous equation. Exactly this equation. And this part, so I'm writing this, and it gives you exactly that.
No, you didn't understand. You didn't understand me. I'm saying that if we ignore the right side of the two equation, we get two homogeneous equations which are exactly the same. We call one of the function f1, call one of the function f2.
Yeah, you have. I agree. You have an inhomogeneous. Why I'm calling this first order? Because I can define f prime as q, and I will get a first order equation for q.
No, I understand.
Right? So you have an inhomogeneous first order equation for in each step of your life, except that you have different inhomogeneous terms. That's all. Good. Now, how to solve such an equation? Let's start with the example, with our example, because here there is somehow, we are somehow lucky. in our specific example, this example, you see, we are somehow lucky. So I'm going back to the example. I didn't manage to really do the calculation in parallel on both sides of the whiteboard, but okay, I'm doing my best. And now I will focus on this using these expressions. So let's write the first, okay, so these are the expressions. Let's implement our y naught, specific y naught, and our specific w. You see?
Yeah.
Here we have a specific y naught, specific v, but whatever it's included, it's everything is in y naught, specific e naught, and specific w. And now let's take the red equation, and let's write it. So I can write it the following way. Minus 2 times y naught prime, which is, so I will have x times y naught times f1 prime. You see? This is the first term of the red when I plug this into. Okay? Minus y naught f double prime is equal to minus x to the 4 over 4, which is my w, times y naught, plus e1 times y naught.
You forgot one.
You can cancel out the line.
I forgot what?
1 in the f double prime.
אינדקס תחתון ליד ה-y.
1. Good. And now I am so happy. Why?
You can cancel
Because
out
the
line.
y naught cancels out.
Yay.
And I have an equation for that I can write as f1 double prime minus x f1 prime is equal to x to the 4 over 4 minus e1. Wow.
But what is the parameter E1?
But we don't know e1.
Yeah.
Okay? And we don't know e1. Now, there is a way that I will show you later on to deal I mean, we still have to take care of e1 and, I mean, okay, it's a good question. Let me explain you what I am doing in this specific case. Again, I'm not pretending to say that I have here,
Wait, you have a problem here, I think.
right? What I am doing in this specific case. In this specific case, you have to look at this equation, scratch your head, and realize that the answer is simply a polynomial in x. Right? And since you have derivatives, right, it must include something that is constant, and it must include something that is fourth order. Right? So you can try an equation. What?
Maybe 6 of them because you have one S1.
Why 6?
לא,
Because you
חמישי,
have-
כי
חמישי,
אף אחד תג יכול להביא על טקסט בריא.
לא, אבל כתוב שם x. No, fourth, it's okay.
Right?
If you have fourth order, you take one derivative, it's 3, but then you multiply by x, so it's 4.
So let's
Yeah,
try.
but F1 double prime.
So we discuss
So
the
we
second
can-
one.
Going on.
Second.
So we check the
זה
Um,
ה-X, זה ה-X.
unfortunately, my solution has disappeared.
נכון.
Let us try. Okay. So, my guess is, my informed guess, is f1 is alpha x squared plus beta x to the 4. No, I would like to call it gamma 1 and gamma 2. Just names. Okay? So f1 prime will be 2 gamma 1 x plus 4 gamma 2 x cubed, and f1 double prime will be 2 gamma 1 plus 12 gamma 2 x squared. Okay, and I plug it there. I have f double prime is 2 gamma 1 plus 12 gamma 2x squared minus x f prime is 2 gamma 1 x squared minus 4 gamma 2 x to the 4. This must be equal to x to the 4 over 4 minus E1. Good. And now I can take care of this equation order by order in x. So I will find that 2 gamma 1 is minus E1. Right? I will find that 12 gamma 2 must be equal to 2 gamma 1. Okay? And I will find that 4 gamma 2 is equal to minus 1/4. 3 equations, 3 unknown, gamma 1, gamma 2, and E1. So we see that gamma 2 is 1 over 16 minus. Gamma 1 is so 12 gamma 2, 12 gamma 2 is 3/4, minus 3/4 equals to 2 gamma 1, so gamma 1 is minus 3/8, which implies that 2 gamma 1 is minus 3/4, and this is equal to E1, so E1 is minus.
No, it's equal.
Plus.
Without minus.
It's equal to minus E1.
Yes, but 2 gamma 1 is minus 3/4.
Yes.
Yeah,
Yes,
so
but
minus
2 gamma 1 is
plus.
2 gamma 1 is
Minus.
minus 3/4, 3/4.
Yeah.
Minus 3/4 is minus E1, so E1 is 3/4.
Yes.
Okay, so we did find the first order correction for the wave function and for the energy. Right? We can write that y is equals to e to the minus x squared over 4 plus epsilon times e to the minus x squared over 4, which was the y naught, right? Times f1, which is
Minus 3 over
what it is. It is gamma 1 minus 3/8 x squared minus 1 over 16 x to the 4. Right? This is the first order correction to the wave function, and E is 1/2 plus epsilon times 3/4. You see? Good. Now, so this was the first order equation. Now what will be the second order? I had this equation, the second order. The second order is this equation. Let's write it. Let's write it here. What is the second order? The second order is and we know that we can use that, right? So 2 again I will have y naught that will cancel out from all the expressions. And I will have minus 2 times y naught prime, which, okay, so this will be x f1 prime minus f1 double prime. It's always it's always the same. It's always the same. The homogeneous part is always the same, you see? Equals now x to the minus x to the 4 over 4, which is the w. Now we have plus
No, it's multiplied by f1.
by f1
Which will
multiplied by f1. Yes, multiplied by f1.
It's minus 3 over 8x squared.
Okay, let's write f1. We know that this is f1. Okay. What's the next thing?
Plus E1.
Plus E1
f1.
f1,
E1 is 3/4, so you can
3/4, plus E2
0.
That's it. Okay. So we have another equation. Okay, let's write it in a single line. We have another equation, and again we
Yes.
F2 on the
what? F2. Oh, sure.
on the left side.
All of the F's.
No,
Right.
no, no, no.
No, those are
Those of the right. This is
No, these are F2.
on the right it's F1.
And
On
the
the
right
right
is
is F1.
yes.
Yes. On the right. Okay. Now we have such a fantastic equation, and now
Also,
it's also going to be a polynomial. However, because of this term will involve x to the power of 8. You see? So what I want to put here is f2 of the form gamma 1 x squared plus gamma 2 x fourth plus gamma 3 x 6 plus gamma 4 x 8. And then by plugging it here, I will get equations for, I have 5 unknowns. I have 4 equations. I will get 5 equations because there is 1 equation for the constant, right? And I will have 5 unknowns, which are E2 and these 4 gammas. I will solve them and I will get the second corrections and so on and so forth. Okay. This is how I suppose to continue. Every,
the question.
yes,
You said that you can use y1 equals y0 f1 up to the first order because you neglected the other solution. Right?
I do not understand. The general expression is
No.
the original form of the differential equation and blah blah here.
Yes, but when you plugged y1 equals y0 f1, you did it because you neglected the other term, the other solution of the first.
This will give me a first order equation in the left hand side.
Sure, but you have 2 solutions and you neglected the other one.
Yes.
You
Yes.
said this one is correct up to the first order. This solution.
This one.
Yes.
Okay.
Don't you need to have the second order when you use the first order of the next stage? You mean don't you need to count for it when you are using the second order of the whole equation?
I did count for it. It appears here and here.
No, but it's still the first order of y1.
What does it mean first order of y1? y1
This
is
term-
the first order correction. What does it mean the first order in what?
Yes, but it's not.
In what
it's
parameter?
It's not y1 exactly. It's
Why not?
approximation of y1.
No.
Because you neglected the other solution of the homogeneous equation.
No, because now we have neglected the other solution of the homogeneous equation.
Yes.
But now we have a first order equation. This is a first order equation, and F1 is the only solution of this equation.
But
There is
for
no other
y-
solution.
But for y1 you have 2 solutions.
Yeah, there is y0 times f1, and there is the y0, the wrong y0 times f1.
But in
That I'm not taking into account because the wrong y0 is not in Hilbert space.
But in the second equation, which is for f2,
Yes.
you actually should have y1, and then you should have two solutions. But you used only one of the solutions.
Yes, because one of them is diverging at infinity. I don't want to deal with it. I mean, I see your point. Maybe there are cases in which somewhere, I mean, it's a good question for people who are, you know, very, very, very much mathematically oriented to find a case where this diverges, but then F1 is converging so fast that it raises the opportunity to use a diverging solution from the last equation and so on. Let's hope that this is not it.
Okay.
Okay?
So we opt for the rest.
Yeah.
What is the motivation to do it if anyway you are taking term by term? So basically you could take the original differential equation and just plug the power series of x and take term by term.
The original differential equation
Yeah, the non-harmonic oscillator, you have like
of the anharmonic oscillator, this one,
you have like
this one,
Yes, just plug y is equal to power series of x. and
power
find
series of x.
Yes.
Okay, that's a different story. This is what I told you last lecture. I mean, the aim of the exercise I did last lecture was exactly to address your question. If you are doing it term by term in x, then first of all, something that I didn't mention, your approximation will become worse and worse as x is going up. First of all, this is, I mean, where here you get an approximation to the right order in epsilon, a global. That's a, I mean, if you look at the book of Bender, he is making they are making a distinction between local analysis and global analysis. So this is global analysis.
Okay.
First. Second, if then you have here some, if you have a function of x which do not allow for a power series, right, like 1 over 1 plus x, then your approximation will break at the point where the Taylor series stop working.
Okay.
While here you have a global, again, it works for any. Okay. So this is the second, what do I mean? Okay. And then you can calculate from this by plugging it, you calculate it. So what I did, of course, I'm too lazy to do that. And of course, I'm not going to waste your time. But I have wrote a very simple mathematical script of a few lines. For some reason, it printed it on both sides, but it's the same thing on both sides of the page. So each of you can take one of these and one of these. Give me one of them just to remind me what is going on. The other one is just, I mean, they are the same.
Oh, wait. So
Neglect one side of the.
two.
Please neglect one side of the page. Either side.
You should have 2 pages.
You have 2 pages,
But he should have the
right?
first one.
You have 2 pages. One is with a few
I-
numbers,
And I give the
and one with
Someone
a.
just
and you
pass
will
me.
forward.
Okay,
Yeah, could someone? Thank you.
okay. So what? Take a look at the first, the one with the figure. I mean this one. So this is just a mathematical script that calculates the corrections using exactly this way up to order 40. Okay? So for each order, I'm defining a polynomial that we start with, you know, 4th order polynomial of only and then we have 8th order polynomial for the 2nd order, and 12th order polynomial for the 3rd order, and so on and so forth until you get, who knows, I mean, order 40, I don't know what the maximum order of the polynomial is 80, right? And the polynomial, you see, f equals sum of gamma I x to the 2i. You see that line? It's the 4th line, right? This is this polynomial, like this one. Okay? And then I am calculating the coefficients of x times f prime. So this is f. I'm calculating all the coefficient of x times f prime plus f double prime. That's the line before, that's AA. And I'm calculating all the coefficients of the damn thing here. Right? And then I'm solving for all the coefficients and finding the and I'm finding what I'm my goal here is not the wave function but the eigenvalue. So I'm finding the correction for the eigenvalue. And you can see if you look at this page that the first correction is 0.75. You see that's a 3/4. And the second correction, no, okay, this is the first correction. I'm not, okay. Fine. And here, and the figure, okay, now I'm, you got finally asleep completely, but I'm, sorry. So now I'm going to your question. I told you, you asked me what I'm doing when epsilon is not small.
Yeah.
Right? So the figure shows you the calculated values of E1, E2, E3, E4, up to E40. Right? This is something that you never see as a physicist. You never see calculations of perturbation theory up to the 40th order. It's something that, right? It's, this problem is nice, very nice, that it allows us to do such things without, you know, calculating 12 zillion integrals, right? So it allows us quite easily to find out. And here you see in this figure, I'm sorry for the, I mean, I have a problem with the colors in my printer. But you see the green one, the blue one is for epsilon equals 0.004. The yellow one is for epsilon 0.15. And the green one is for epsilon equals 0.4. You see? Now, what you see is that the numbers are going down, but then after a while they go up. Why? Because this is an asymptotic series. It's not a converging series. If you now calculate, you know, all these terms, right, you will get infinity. And note that the, no, I'm not saying that. Okay, this is the point. They are growing up. Of course, I can take epsilon equals 1, but what will be the problem? It will shut up so fast that you will not be able to see that. And you can see also that if you are trying to implement optimal truncation, right, then in the epsilon equals 0.04, when we are close to the epsilon equals 0, we can take something like 8 terms, right? In the epsilon equals 0.15, we can take 4 terms, and in the epsilon equals 0.4, maybe 1 term. So of course, the optimal truncation technique is getting worse and worse when we are going to higher and higher values of epsilon. So what one should do?
Wait.
Okay.
The X line, the X line is the number of terms you can get, and the output is the.
Yeah, that's E1, E2 up to E40. Very simple. And because this is a diverging series, of course, if you want to extract information directly from the series, you have to do optimal truncation. And you see that the optimal truncation is getting worse and worse, is allowing you to take less and less terms as epsilon is going larger. However, what you can do is to padate, right? The way I explained 2 weeks ago. And once you padate, which of course Mathematica is doing for you, you don't have to work hard, pade approximant, right? You write pade approximant, and now I did, as I told you, I distinguish between the P00, P11, P22, the NN, and the NN plus 1. The the even and the odd Paddy approximant, and as advertised, first of all, and now you see the sum of the Paddy approximant, right? The estimation that Paddy gives you. So do you see that the for this is when epsilon is going to x, but what is the hell is x? Did I define? Yes, x equals 1. Okay? So this is for epsilon equals 1. Okay, you see? This is for epsilon equals 1, which is, when epsilon equals 1, these points, the ENs, are growing from the beginning. It's horrible, right? In epsilon equals 1, it is going like that. But if you will Paddy the series, it converges as fast as possible. After the first of all, as I told you, the NN is converging from above, the NN plus 1 is converging from below. So they give you, in any case, they give you lower and upper bound, and you see that they converge to point.
Point 3 it looks like.
Point something 303 303 plus minus 303 plus minus 0.002 or something. Here is a list. This is a list of so they converge so fast, right, to the correct, and you get the correct answer from actually, in fact, you know, the first 10 terms to the fantastic accuracy. Right, and it's about 0.3. There is something I don't remember here. Yes, this is what I'm calculating it, and what I'm showing you here is not E, but E minus E naught.
The correction.
This is the correction to E, right? It's not E, it's E minus E naught. So E minus E naught is at epsilon, E of epsilon equals 1, right? Minus E naught is point what? Point 03 or something.
No. It's 3.
Point 303.
Yes.
Point 303. So E is 1/2 plus that. So it's 0.803. Right? You can calculate it very easily once you have this opportunity. And now, of course, you understand what one's supposed to do. So any perturbation which is just a power, right? It will be solvable that way. Right? Okay. Okay, as I told you before, the fact that the Paddy approximant converge, this is guaranteed for any Stieltjes function. So you have to believe that E, you have to believe that this quantity, E minus E naught, right? So this quantity, let's call it E tilde of epsilon, right? This quantity is a Stieltjes function. And this is the reason why you have to subtract E naught, because E naught, you remember in the Stieltjes series, the terms must come with the alternating signs. But E naught was 1/2 and E1 was 3/4. So they have the same sign. But these are the last, I mean, E2 is minus, E3 is plus, so you have to subtract E naught and then Paddy. That's the deviation from E naught, which is a Stieltjes function. Not the energy, but the deviation from the zeroth order energy. And now but as I told you, it is once there is once it is stilgies, we know that the Padea approximants will converge, but it is not sure that they will converge to the right solution. They may converge something like that, right? Which I guess is what's happened if you put instead of x to the 4th, x to the 8th. But you can try it. Okay. Now, all that was for, so you see I did something that was completely generic, and then I switched to this example. This example was especially simple in the sense that it allows me to guess a polynomial, and once I have the polynomial, by calculating all the coefficients of the polynomial, I can address both the E naught problem, both the corrections to the energy and the correction to the wave function. I can find both E1 and F1, E2 and F2 at the same time. But this is the grace of God. This is not the generic case, right? This is luck. This is pure luck, because if your W is not x to the some power, but if your W of x is 1 over cos x,
You won't be able to define.
you won't be able to solve it using polynomials. So the generic question is not solvable this way. And now let's speak about what you're doing in the generic case, which is of course much more difficult. And now if you wanted to calculate the 40th order correction, then find a good, very good friend, or work very hard to make this problem accessible to some code, because it's not simple. Okay, so what we are doing in the generic case, we have ended up here.
אתה לא יכול לתת לה את הבעיה לדוקטורנט כדי שיפתור לך אם אתה רוצה לחשב רק...
No, okay, the rule is like that. If you are a physicist, you are doing only first and second order perturbation. First and second order corrections. No. Sorry. You deal with a problem, right? If you want to do perturbative expansion, you give it to your student, right? And if the student is doing second order perturbation, then it's nice, right? Third order, I told you, what was his name? I've forgotten his name again, but I told you the name. I guess Kondo. Kondo got the Nobel Prize for calculating the third order correction for a certain problem, right? Because nobody had the guts to do that.
הם פשוט ריחמו עליו, אז הם אומרים ניתן לנובל.
מה?
זה לא בן אדם שאחר כך הלך ליער וירה לעצמו בראש כי כל החיים שוריס וזה ל...
לא, זה מי שפתר את בעיית המילניום.
מה? לא שמעתי על זה. אוקיי. הלך ליער וירה לעצמו בראש, זה קטע של סופרים, לא של פיזיקאים.
הוא היה מתמטיקאי.
מה?
הוא היה מתמטיקאי.
גם מתמטיקאים לא אמורים לראות.
אבל זה מיתוס מסתבר, הוא פשוט הלך לגור עם אמא שלו בבית ביער. לא יודע אם זה יותר טוב.
זה לא מתאים למתמטיקה.
לא, היה את הגרוטנדיק הזה, שהבן אדם מבורבקי, שעזב הכל ועבר לגור באיזה בקתה, אבל הוא כנראה השתגע או משהו מיני. כמו ג'ון אש, כאלה אנשים. היה זה, היה ג'וזפסון.
שמע, זה לא שאין פיזיקאים שהתאבדו. גם בולצמן וגם ארן פס התאבדו אחרי שהם סיימו לעבוד על מכניקה סטטיסטית.
כן, גם טיורינג.
זה משהו אחר.
זה התאבד מסיבות אחרות.
זה לא בטוח בכלל. זה סתם, יש, סביב טיורינג טבעו הרבה זה שאני לא בטוח.
כמה ליברלי.
אוקיי. מה רציתי להגיד? לא שטיורינג התאבד. Back to work. We have the work to do. Once, many years ago, the Israeli Academy of Science hosted a lecture whose title was why Boltzmann and Ehrenfest committed suicide while Einstein and Maxwell did not. I didn't hear the lecture, so I don't know the answer. Okay, so we ended up with, right, for example, in the first order, we ended up with the red equation written here. Okay? Now, how we proceed when w of x is a generic function? The answer is, we multiply everything by y naught. So what we will get is, let me write it in red, such that it will be clear that we're continuing the same thing, minus 2y naught prime f prime, minus y naught squared f1 double prime is equal to minus w of x y naught squared plus e1 y naught squared.
You forgot f1 in the first
What?
term. The first term you should have 1 in the
Index
F prime.
of
F1, yes. Now there is a miracle because these two things are simply y naught squared f1 prime with a minus.
It's some sort of integration factor?
Yes, like
Okay.
you use y naught as an integration.
Yes.
And this is equal to w of x y naught squared plus e1 y naught. Okay,
minus w.
so y naught squared
And it's minus w.
minus, yes.
You can
And now the
Integrate.
point is that I will integrate both sides of this equation from minus infinity to infinity. Okay? Now, this is a derivative of something. So its values at minus infinity, so the answer is, forget about the minus, put the minus outside. This is a derivative of derivative, right? The integral is a derivative, so the integral is the function itself. And we know that the function itself goes to 0 at plus minus infinity. So this is gone. Okay? So what we have obtained now, after integration from minus infinity to infinity, we obtain integral from minus infinity to infinity of w of x dx equal w of x y naught squared dx is equal to e1 integral from minus infinity to infinity of y naught squared dx, or we find e1. E1, if you remember now the quantum mechanics that you have learned, you first find the energy and then you find the wave function. And with this, you go to the next step. So this is what we did here. Right? We find the wave function with the corrections to the energy, which of course is simply, this is, okay, y naught squared dx divided by the integral from minus infinity to infinity of y naught squared dx. Just to remind you, this is simply psi naught h1 psi naught divided by psi naught psi naught.
Psi naught, but it is 1.
What?
Psi naught is 1.
For normalization, it should be
Normalization.
What?
For normalization, psi naught is 1.
So okay, so now, but since we have we are dealing only with homogeneous equation, so only with linear equations, we never determine y naught, right? So y naught is determined up to a factor. A y naught is also a solution. We have a linear equation, right? So in this way, you make sure that, I mean, this is like normalizing the wave function. Okay? So this allows us to calculate. This allows us to calculate what? To calculate the first correction to the energy. Okay? What?
You can plug it back there.
And now once I know E1, then I am going back to this expression, and I'm taking out the integration, right? And I can solve this. Now this is an equation for f1. I can solve it with two integrations. So I can say that now y naught f1 prime prime, right, is equal to w of x y naught squared plus minus e1 y naught. I know both.
Y naught
Y naught squared. I know both this. Right? So I have two integrations. So the first integration will give me y naught f1 is an integral up to x. This is a function of x.
Y naught f1 tag.
f1 prime, yes, is an integral up to x of w of t, y naught squared of t dt minus the integral up to x of e1, or the e1 is outside because it's a constant, y naught squared of t dt. Okay? Now I have to divide it by y naught and integrate once again to get f. So f1 is the integral up to x of the q, say 1 over y naught of q, integral up to q of w of t y naught squared of t dt minus e1, again integral up to x dq y naught of q
Q, not to X.
up to, no, the outward is up to x, and then the inward is up to q of y naught squared of q of t dt.
The integration is from minus infinity.
Okay, first of all, let's agree that this is a solution, right? Because when you take a first derivative, you have to, a first derivative of according to the boundary is just the integrand. So you forget about the q, you have this, right? And then the second, and q becomes x. So you get this, and so on and so forth. Now, what are the boundaries? So the
shouldn't it be y naught squared? In all of
well,
them? All of them. Because
No.
because over there it is y.
yes, this one is squared.
Oh, yes.
Okay,
This one
okay.
is squared, and this one is squared, and this one is squared, and this one is squared.
Okay, thank
Yes.
you.
So, sorry. Thank you very much. Okay. Now, what about the okay, now if we want f1 of, what do I need? No, okay, this is, let's put it to be A.
But then it will be
So
minus.
A is a point where f1 is 0. For example, in our f1, they all were 0 at 0. So A is a point where f1 is 0. Okay, now this was the first order. Okay, now the grand finale is to write what you're doing, what are the formulas. But I mean, there is absolutely no point in writing that because
There is not enough.
if you will need to implement this formula for the fourth order correction, you are going to open the book, right? But just to Okay, as I guess, you see, it consumes all the lecture, and I didn't have time, and I don't have time for more. So the generalization of this horrible procedure is that En is, so I have to, first of all, here I have the integral from minus infinity to infinity of y naught squared dx. And what I have here is the integral from minus infinity to infinity of w of x y naught square of x dx. No, it's not y naught squared. It's y naught times y of n minus 1 of x. dx minus sum from j equals 1 to n minus 1 of ej, because you need all the corrections up to here in order to get this correction. And now you have the integral from minus infinity to infinity of y naught of x y n minus 1 of x n minus j of x dx. Right? This is the general expression for the, again, the only thing you have to remember is that you have to implement all the energies, the corrections to the energies that you find until now, and all the wave functions of the lower orders, right? And now you want me to write the horrible expression for okay, so yn of x is this is just the beginning of the horror. Well, let's assume that all the wave functions are normalized. Something is wrong here. But okay, who cares? I mean, we've exhausted our time. So essentially what I want, I mean, you can always look for this formula in the book. Nobody remember, I mean, why I'm saying nobody. I don't remember such formulas. But I hope that you've gotten the main message that I've tried to deliver here, is that in Schrödinger-like equations, we have to take care to develop not in a single parameter y, but two parameter y and e every time. And the way of doing that is to make this substitution that makes the problem, what's the name of it? That y naught times f, right? Reduction of order, the reduction of order. And then we are getting first order equation with which we can deal either formally or in the case that that we used an example, we can deal it exactly because we get a polynomial equation. And now the answer will be a diverging series. The answer will be something that at some epsilon, at some order, for each epsilon at some order start growing to infinity. And the way to get rid of it is to pade the solution. Okay? Thank you very much. And so I'm still owing you the first three examples of perturbation theory that were aimed at making clear the distinction between singular and regular perturbation expansion. So I didn't do it here, but next week I will return to it. It's not a big deal. Thank you.
Let's start from something that you already saw in previous lectures, and I think I talked about that a little bit in previous tutorials. It is basically the concept of small parameter in equations and in ODEs. Practically, it's what will bring us to do perturbation theory. Okay? So I will write, this time I will do things a little bit in different order than what I usually do. I will not start from writing the definitions, because I think the definitions will pop out of the actual examples and equations, and it will be better like that. So it's more like there is no actual formal way to define things there. It's more like something that you need to look for it and do the right steps in order to find it. There is no formula to do that or anything that, okay, first step, second step. There is some ways to do that, and I will present that, but sometimes it will be totally different. Okay, so basically what I will start to do is have some nice introduction to perturbation theory, but I assume everyone here do or did quantum mechanics too. You already heard about perturbation theory in quantum mechanics too. So I'm skipping the motivation and the introduction. You already have some motivation to study perturbation theory. You know why it's good, and practically what we will want to implement that. Practically what we will want to do is to implement that in other field than quantum mechanics and explain that. I think this tutorial do it well, but I'm keeping it simple for this tutorial because it will get soon out of hand because we will start to do some crazy stuff of on perturbation theory. I think from here to one lecture before the end of this semester or something like that, we will do perturbation theory, and in the last lecture and last tutorial it will be integrals. So practically what left is perturbation theory, and this tutorial only presents the basics of it. So let's start from writing the equation. So example 1, it is epsilon y to 3 primes plus, it's supposed to be epsilon squared, epsilon, let's write it, pi prime equal to y. So that is the first example. It pretty much summarizes what you will expect to see.
Y triple prime or Y double
Triple
prime?
prime, yes.
No, because it's not clear. Can you? I'm not. Thank you.
Should be epsilon squared or just epsilon?
It should be epsilon squared.
Because in
Yeah, that's what I said. I have typo in the tutorial notes. I will upload, when I will have Wi-Fi, I will upload just add in a square, so I will not be lazy this time. Actually, last time I rewrote the last question, physical question, on the viral expansion to ideal gas, to actually non-ideal gas. And now it's fixed and uploaded the new version in the Lambda, so you can look for it, look on it. What we will practically do this time is remind you some things that will be helpful in those sections of perturbation theory, and then we will continue because, okay. So when you encounter problem like that, just a recall from our first tutorial. What is the method of solving that problem?
Power series.
Power series? Yes, you agree?
for y or
No, actually the method, recall. Method of
It's flowing order.
constant coefficient. I think that is how I write it. Okay. So practically what we will do is substituting y equal to mu x, right? Because all the coefficient to y and y primes are constants. Then what we will get is epsilon squared mu to the third power plus epsilon mu equal to 1. I'm sure everyone in this class know already how to do that. That is not new to you. So, yes, everyone know that? Okay, good. So now, from conservation of hardness of the problem, we still got third order polynomial equation, and we know how to deal with degeneracy of the polynomial equation, and we know how to deal with everything is the same. And we actually know that the solution, there is closed form solution to polynomial equation until fourth order, and from quantic, quantic is fifth order, and so on, because of some group theory stuff that I'm not willing to explain here. You can't find a closed formula for fifth order polynomials. So that is actually the solution, and we can find it exact, but we don't care. You know how long will be the formula for roots of third order, third order polynomial in general? It's have something like 27, I think, terms, something like that. And roots upon cubic roots, that is horrible. We don't want that. if you're a good physicist, you will take first two terms and finally you got the solution. So how we will deal with that? You already know. Perturbation theory, right. So what you will want to do is find all the roots. What are the two types of roots that can be in that problem? Epsilon, just to say epsilon, when epsilon goes to 0, it's necessary to say, okay? Sometimes it will be even with which side it approaches 0, it can have totally different behavior because of some singularity and all of those stuff. Have you saw that in lecture? No. Okay, you will see that. But remember, sometimes you have plus or minus, all of those stuff. It can be important. Okay, so there are two types of roots to perturb equations. One that diverge, that mean when epsilon will be 0, they're practically at infinity. And one that converge, that when epsilon goes to 0, it is converge. You can see from here, okay, let's start. What would be negligible in that equation?
First term.
First term, that term?
Yes.
Actually wrong. That is, I hope someone will say the first term is negligible because there is epsilon squared.
But mu
that-
is have to go to infinity
mu-
in order to
Yes,
solve the
the
equation.
problem is that you need to start with smelling the problem.
Ah, okay.
If it smells a little bit fishy, you know it will have some
I think that,
exotic properties. Oh.
I think that for consistency, the epsilon mu should be negligible in order to...
Epsilon mu should be negligible.
Yeah.
Okay, yeah, that is the solution. Yeah, but if Dima said that is negligible and they say no, you're wrong, and then what's left, that will be negligible.
No, actually,
Okay,
you can
yeah,
neglect,
I
no,
understand.
you can neglect the 1. You can also neglect the 1.
Neglecting the one.
Yeah.
Okay, it can happen. You're right, but not in this case.
No,
You're
in this
right.
case.
You're totally right. There are cases that you throw away the constants, but it's most of the time in that all of your solution diverge, and you are diverging faster, or something like that. That's what it means. But most of the time you want to bring your equation to something that look like that everything is converging, all the coefficients. That is the best rule I can give you. That is classical equation for tests. Schnell really like to ask question like that. Here, take that equation, and you have literally no convergent solution, because if you will substitute epsilon to be 0, you will find 0 equal 1. So there is not existing solution for epsilon goes to 0, so it's actually very strange. It's not a polynomial equation for epsilon goes to 0, it's something strange. But there is a solution to something like that, and those stuff appear a lot in physics. You will find that in third order, second order, and you have a lot of those stuff. So what we actually will want is to understand what is the scale of the problem that it's diverging. No one say that it will diverge like 1 over epsilon, right? There is no reason. You can think maybe for reasons why to guess something like that, because every power of epsilon is a whole power and nice and integer and a lot of stuff, but the point is that doesn't have to be like that. So how to start? Practically now we will go to, after you understand the problem, that what looks like intuitive to just throw away here, it's epsilon squared. We can throw it away.
We also assume that mu is a function of epsilon.
Yeah, sure. Epsilon is given number. There is a solution. It has to be dependent. Okay, it should depend on epsilon. Sometimes you have some degeneracy. If, for example, here instead of 1 there were mu, because that were y prime or something like that, you will have epsilon equal to, I'm sorry, mu equal to 0 also as a solution. And it's not depend on epsilon. You can say depend on epsilon, but it's not epsilon in the solution, the actual solution.
You can do what we did in the first lectures and tutorials, and use dominant balance to find.
Yes, what we will do is dominant balance and all of those stuff. But what I'm trying to say is you have something that is more I don't know how to call that. It's a concept that you have to understand, that every problem has its own scaling. And here it's divergent, and you want to find what is the scale of divergent. Unfortunately, here I will tell you already, spoiler, epsilon, 1 over epsilon, intuitively students guess in the test that is how it's diverged, and it's not right for that case. But how do you find that? That's what I will do. Wait, I don't want no questions. I will do it, and after that I will formulate what I did with a definition of the scaling. It's called width of a problem. I think I said that a couple of times before, but today I finally agreed that okay, I should define it to you. You have to know that. If not Nadav will. If Nadav is not doing that, I will do that, because that will help you understand and have some intuition on problems. And when we study perturbation theory, it's must to have that intuition. Okay, so I said a lot, and now let's do some stuff. What we actually want to find is something that diverge. So mu, we will set it to equal to t over delta. Delta is small parameter. It's more, for me, it's more intuitive to work with small parameter, but you can actually set mu equal to lambda t when t is in the order of 1, okay? And here lambda is very big parameter, and here delta is very small, but 1 over delta is like lambda, it's very big. For me, I like to work with small parameters, because I like to neglect things that are small. But sometimes you don't have the choice, because you can divide, or it's in exponents, something like that. So you need to really know how to do also perturbation at infinity, but it's pretty much the same, and you will study that in integrals, and you will see that over and over and over and over and over to the end of that course, pretty much from now. So let's stick to that. So if we know there is no converged solution. If there will be converged solution, what will be my guess? I will have to find something that look in order of something like that, or something that t0 plus delta t. That will be our width. What will catch the asymptotic behavior of the solution. So let's substitute that to our equation. If you want O of t, I don't know if it's right to write it like that, but you understand me? It's equal to O of 1. What will be the derivative of O of t? Okay, so what we find here, we will substitute that. We will find epsilon squared delta to the third power, and not mu t. We understand that both equations are equivalent, totally equivalent, and their hardness is equivalent. There is nothing special in one. There is no difference between them. But one is actually, if you want, delta is also in scale, the same scale of t. If you want to think about that, actually, delta can have all the units of the problem, or it can be unitless. You can choose that, and what you will choose will actually bring out the. It depends on actually how you will choose delta to be. Usually you choose delta that have units, and t is unitless because it's nicer to work like that, unitless stuff. But your choice here really matters. It's what you will define. It's actually defining your x-axis or something like that. You can think about that. What will be the gap between each how that called? You have the scale of the x-axis. Okay.
משבצת?
Yes. Every cube cell in the cell in the grid when you are plotting something. Okay. So, what our choice here for delta? We can actually try stuff. We can say, okay, we don't like the epsilon over delta or something like that. We want something that will be small for sure. So let's start from multiplying by delta, all the equation, because it looks smart. Why I'm doing that, I don't know. There is no formula. It's actually, from here you're alone. But who says it's not delta ln delta? Sometimes is the right guess. For example, if you want to find perturbation in incomplete gamma function, that is actually not bad guess. Actually, the best guess will be delta that is minus, that is something like that. And that will be amazing. You will find immediately the solution, I think, for the incomplete gamma function. But for our case, let's continue. Then epsilon
Delta squared. You said you multiply by delta, right?
Let's do it different. Okay. I'll do it differently because okay. Also, I did something in my head. It's all of what you're doing is practically guess and try. You need to validate yourself. So here I have I changed the solution that I will present because it will be more intuitive. We have two variables that we need to control how they're diverging or converging and all of those stuff. We have practically two expressions that we want they both to be finite. One of them can be small, and then we will be able to neglect it. But we want a condition on delta that will not be too strong, so we will have practically no solution to that equation, and to not be too how do I say it? Too weak that we will have still explosion in our equation, or some convergence to something that doesn't have a solution. The delta that we will find is called the width of the function, the scale of the system, whatever you want to call it. So let's try the wrong one. We already know. Epsilon over delta, we will guess that it goes like 1. It's the same order of 1, so delta is on order of epsilon. But what happened here? That expression will be in order of 1 over epsilon. It's exploding. That is bad. So that is not good. Delta will be for that expression in order of epsilon if we will want it to be in order of 1, and then that will be in order of 1 over epsilon, really bad. But in that case, if we will take the condition that goes like 1, we get that delta is in order of epsilon of 2/3. Right? So we practically here, delta, we just add a constant. Now we have enough degrees of freedom to set it to actual parameter. You don't have to keep constants. I actually recommend you don't keep constants, because the constant that will pop out will actually show you what is the physical meaning of the system most of the time. But here it's very simple. We set it like that, and now what we do is practically saying, okay, now we have an equation, not with mu, with t to the 3rd power plus epsilon to the 3rd power
To the 3rd or to 2/3?
to the 3rd power, 1 over 3.
1/3.
1/3. And here we will have 1. So now, actually we found what will be a nice expansion of the perturbation. A nice expansion will be in order of epsilon to the 3rd. It's still a small parameter, but it's much bigger than epsilon, right? Because epsilon is very small. Taking cube root, it will be much bigger. Like 1 over 8 is compared to half. It's enormous. You have enormous gap, right? 1 over 27, and compare that to 1 over 3. It's crazy. 1 over 64, and compare that to 1 over 4. You see how fast it's grows.
You want to prove more that you know the powers?
Okay.
Of,
I want to continue. So now I can actually start doing real stuff, I will call that. Now I can set t to be expansion of what? an sum of n epsilon to the 1 to the n over 3 power. And that will be the nicest way and the fastest way to find the solution. And look what we found here. Now we will just have to divide by delta, and we find a perturb. We find a perturb solution to t, find a perturb solution to mu. And now it's much easier, right? Because we find the scaling of our problem, how the first mode is diverging. Actually, a better scaling to the problem, we can maybe call epsilon to the 3rd power be our scale, and delta is defined to be our width. Okay? Sometimes it's a little bit blurry, the definition and the notation. It's actually not written. It's supposed to be written in my tutorials, but that thing, it's something that writing in words, it's very hard, and I don't want to do that. It can be a little bit blurry, the definition of width. Mathematicians define that with measure theory, something that only third-year mathematicians study. So yaks, let's throw it away. And physicists just say width on everything and scaling on everything that looks like a scale of the system. Here the actual scale is epsilon to the 3rd power, but okay, wait a second. But delta is the width for that example. Yes.
How do you find the AN series? How do you find
That's what we will do right now. Okay, so let's first doing the perturbation now. T0.
Erdan,
What?
I have a question.
AN,
What?
let's call that TN.
Why is better than just dominant balance?
It is okay. You find the width of the system, that is something that gives you some intuition on the system. Why it's better? It is practically here I found how to take a sum of what is the scale of the system, something that from dominant balance I can't do, right? No?
Why do they need T?
You can do it
I
with
don't
dominant.
understand the whole,
Okay,
the whole
okay,
point
you can.
of it, so
You can. What I'm saying is, doing with dominant balance is okay. Totally okay. You will get all the points, and I'm sure that Snab is doing that with dominant balance. What I'm doing is introduce you to another method of do that. That, in my opinion, give you some intuition and insight on the problem. I really like to do that because in that way you find. Here I found what is the right epsilon to do the expansion. That is nice. You're not able to say that is the right expansion of mu to say mu from sum of n, mu n to epsilon to the n over 3. And you actually don't know from where to start that summation, right? You know that goes to infinity because you want it to be infinitely correct, but you don't know where it starts. But here I really know, because here for t it starts from 0 to infinity, and the only thing that I have to do is divide by delta squared, that is pretty much divided by 2/3, that means that n here goes from -2. You cannot infer that from dominant balance. Okay, you can find the first step and second step and then infer the scaling of the system and all of those stuff. But here you can do that just from that assumption and find that very quickly. In my opinion, it's easier. You can choose and do whatever way you want. I will show more examples, and if it's not clear why I think it's nice, ask me by the end of the lecture, and I'm just showing you another way of doing that. Okay, that's it. If you don't like that, you can use dominant balance and whatever you like.
how we got epsilon in such a power like n over 3?
I just plug what delta is, and delta is epsilon to the 2/3. So epsilon divided by epsilon to the 2/3 is epsilon to the 3rd power.
Yes. Then you wrote the series.
And then I just say, okay, from here I can actually do the perturbation theory. Why? Because it. Okay, from here, if you want, I guess the full expansion of that. Why here I can guess that? Because my leading term is 1. Here it's not 1. That should be red alarm to you that you have something that can goes a little bit fishy in the problem. When the dominant term at, for example, mu goes to infinity is not 1, it's not a number. Here it is a number.
The question was about.
That means I caught the leading behavior of that. Yes, I'm
The
sorry.
question was about power of epsilon in the series. Why did you pick n over 3, not just series Tn multiplied by epsilon in nth power?
Yes, from that equation, that's what I said. That here I see that the dominant term, I will call the dominant term, the highest order term, t to the third power, is 1. So I can relieve. Here I need to stay in focus and be with a lot of senses to sense what happened here, because in this equation the coefficient of the highest power is approaching 0, and that can give you a lot of shenanigans in the system. Okay? Here the dominant term coefficient is 1. So here it's much nicer, and what is the width of the function? Epsilon to the third. Why it's like that? I don't know how to answer to you. Sometimes you can actually, if here for example we had epsilon to the 1/5 or something like that, maybe I will guess another expansion, because I will have to take 2 expansions, and that can happen for sometimes, but you're not with Kessler, so we will not see that in test probably, I hope. And Kessler liked those edge cases. And then what we are doing is practically 5n minus 4 divided by 5n. Why I'm guessing 5n? For reasons that if I had something like that, I will guess something like that, or something that looks similar to that, because I will think, okay, and maybe we need crossing terms and all of those stuff, so maybe smart to guess that epsilon goes like 15n, and then we have one sum, and finding the first 4 terms can be a little bit of brain damage. Yeah. So why I guess that? Because I have a lot of experience. That is the short answer. That the bad tutor will say. Okay? So I will be a bad tutor and say, because I have a lot of experience. But that is actually the case, because there is not a formula to how to do that. You need to see some examples, and then you will be able to do that also. Okay? From a lot of practice, and you will get that. Okay. I'm good with time, actually. So here we want to find t. If we find t, we won. We know mu. T0 is just the tube equation. Is t0 to the third power equal to 1. Remember, for third order polynomial equation, you expect 3 solutions that can be degenerate also. But remember, because each year the amount of points that lost on equation like that people forget about complex numbers are crazy. I think if you do that equation without finding complex, with just say t0 equal to 1, that is the solution and only solution. If the question is 30 points, you will get something like 15 maximum.
0.
Practically, yes. Because that is, undergrad studies will tell you how to find all the solution, and it's like missing more than half the solutions. And if missing a solution is the worst thing that you can do in a test. If we want to find a solution and you didn't find even the amount of solution to that equation, you didn't find all solutions, and that is very problematic. Okay, you understand what is the problem here? It's, I actually missed 1 solution in my test for regular singular point, but find it accidentally, so I added it and didn't know what I'm doing, and Kessler didn't like that and gave me 0. That hurts, but with factor of 16 you're fine. will be factor of 16 points. Okay, so the solution, I recommend you to represent it like that, e to the I power 3 k, when k is in 0, 1, 2. It's very elegant way if that were t0 to the second power, to the power of 2, you will do plus minus. That case practically the generalized form of doing that plus minus, and it's save you a lot of time, because if you ask to find the solution to the order of epsilon squared and you need to write that for each solution, it will be horrible. But if you write it like that, it's just chick-chack. Yes, exactly.
It's fast in Hebrew, right?
What?
It's fast.
Yes,
Yeah.
that were a joke.
Yeah.
It's like really,
Yeah.
really fast.
Yeah.
I did that on purpose, so don't blame my
Okay.
English. It's already bad, but you have many more things to find that is bad. Okay. So now, doing second order solution, if you look like that, what will be here? T to the third power from Taylor expansion, or just throwing that everything that's smaller than epsilon to the third power. What we will do?
אפס בשלישית שזה 1,
T0 בשלישית
ועוד
plus
T1, כל השאר.
epsilon
אפסילון
to the
T1.
third power times 3, T0 to the second power, T1, plus here we have epsilon to the third order, T0, because multiply the first term it will be negligible, and then 1, then that goes with that, and now just divide by T0 and divide by epsilon to the third power, and what we get is 3 T0 T1 plus 1 equal to 0. Then T1 is minus 1 over 3 T0. Exactly. Then I continue to something like third power, but it's very easy and very quick because it's polynomial. You find t, you find mu, therefore you find mu, therefore you got everything you need, and you won because you solved the solution. But you've solved the problem. That is one representation of a problem that can appear. How to find the convergent? It's practically the same. Just you substitute. Here you assume that your solution is diverging because you want delta to be very small. But for convergent, like I said before, you guess delta times t.
Wait, why did you say that T0?
You have a question?
Yeah. How did you get that T0 is e to the I pi third k?
Solving equation.
What was
First year complex equations. It's even taught in school. Final test, you have that guess the solution of RE to the I theta and solve the problem. You're graduate students here. Okay. You're not graduate, right?
No.
It's okay. It's first year, I'm sure that you will be able to understand it, but if you don't understand it, come to me after the tutorial or ask me after that, because I don't want to, that is not, you don't have enough time to show also how to solve things regular. Okay. So let's do another we practically understand how to find the width from that. For example, like that, you need just to guess the right quantity that will represent your problem. If you have small parameter on an exponential, you can guess ln. It's practically something that we will recommend. Or if you have something inside a ln, you can expect. Actually, you don't need to add anything else most of the time, but because exponential, it's like exponential of delta is like 1 plus delta.
No, I actually remember there is no.
Okay, it's okay, but don't interrupt me when I'm talking. Okay? Only if something that I said is not clear. Because I'll just go, I have קשב וריכוז. So if you cut me when I'm talking, I will forget what I'm saying, so please, no.
What we do now, it's a global analysis, right?
Global analysis, yes.
We don't care about X, we're only looking at some parameters that can be small
here we guess a global solution, right?
Extremely large.
Guessing that is guessing a behavior that globally happens, right? It's global solution. I say that for all X. I didn't say that until now. We say, okay, when X is approaching X0, and we had a lot of things and phenomena that appear only for local analysis, like Stokes phenomenon, and a lot of things that happen because of local analysis. Now we are doing global analysis. It's totally different thing.
I agree, but the problem is that you wrote only one solution, but the equation is third order. But
we find 3 solutions because you have 3 options to K. Yeah, that's what I say.
Okay.
That is a compact way to represent a solution. If you will not do it like that, and you will find that will be awful. Don't do that. Write that nicely like that. People that will write for each K, they will just suffer in test. Sometimes you have to define for cases like even K, odd K, the K that divide by 3, K that divide by 5, because you have some exotic cases that can appear that something will be 0 in one case. For example, if you have 1 plus e to, I will give the simplest case, like something like that, plus ta 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 ta, and k is 0 or 1, okay? K is Boolean, okay? What happened here is that you have to do each case, actually, you can divide by that, can't. Why?
Sometimes it's 0.
It's 0, yeah. And then you will have to do that by hand. So plus minus will not work. You will, because you can divide by that. But that is very degenerate case that lecturers that want to fail you in the exam put and see who fall into that trap. It's not that hard trap to avoid, but it happened, and it's happened sometimes, so you need to be aware of those edge cases. Trust me. But in Shinab exams, something like for every 3 tests, you have some trap like that in random question once. And if you find that, you have one exam of him, something like 5 years ago, that he put too many traps. But be happy, because last year we had tremendous amount of traps that appeared for the first time in tests. So they were not hard to spot, but that is tough to. you need to guess that, okay, it's really a trap, yeah, it's a trap, and we never saw that before. There's so many traps.
Do you have an example of a trap?
Yeah, just show you. Example that you can write things in general or something like that, that you have to literally solve for each case because it behaves asymptotically not the same. That is why it's appeared and it's so awful. And now I will try to find next correction. I think I have mistaken calculation, but I don't care in the tutorial notes. Epsilon x to the n plus x. That is our next equation. Do you feel comfortable with that equation? No. Why? What bothers you? Yeah, the epsilon before the x to the n. If the epsilon were here, we can relieve and we will can be chill and okay, nice. But in that case,
for large n, radius of convergence will be extremely small. That's why.
For large n.
Yes.
No. We're not taking n to be large and no. What is approaching 0 is epsilon. Actually, in my test we had epsilon that approached infinity and that were mindfuck. So I said, okay, epsilon equal to 1 over delta. And then it were nicer. If someone gives you epsilon that approach infinity, put a mask on that epsilon, you don't want to see him, and only at the end substitute the solution. Promise me that will save you some time in test. So, what can we do in that? What is the first step that we will do? Let's find in converged solution because it will be very easy. We will guess a converged solution that will be in order of epsilon, right? X solution, let's denote it with C for converge. It will be something that goes, in that case, when epsilon is 0, it's actually very easy to spot what happened. So let's write it like that. And we have xn epsilon to the n. Why now I'm taking epsilon to the n? Because when epsilon is 0 I have solution, so I guess that is the behavior. You can find that with just say delta t and multiply everything and balancing, and you will find probably what you need, but forget about that for a second and let's focus. That will be the main thing. Why? Because it looks like that. If you need to verify that, depends on the question, and sometimes the whole point of the question is just to let you know that there is another term of a ln. Ln is the index. A ln epsilon ln epsilon. When epsilon goes to 0, it still goes to 0, but it goes to 0 slower than epsilon and faster than epsilon. Sorry, slower than epsilon squared and slower than epsilon squared, and even and faster than epsilon. It's like what I meant.
No, it's slower than epsilon.
Yeah, it's slower than epsilon,
So you're multiplying by
and epsilon is smaller. Epsilon squared.
אי שוויון הזה
Oh,
רק
yeah.
לאפסילון גדול מאחד.
Yeah. And yeah, that's why we're confused for a second. It's just adding another perturbation step, and it can happen. You have a lot of degeneracies, and it usually happens when you have e to the something, and some edge cases that we already saw degeneracy in equations, and if you smell degeneracy, that can be one of the terms. And I hope you will spot that when it happened, but it could happen. I know one example in the incomplete gamma function, and I have really nice example with integrals, but we didn't study integrals, so I don't know how to present that for now without integrals.
What do you mean by degeneracy in such case?
I'm calling that degeneracy, but it's not.
It's
Don't catch me on the words. It's not.
It's not
It's not
differential equations, just
No, it's some.
ordinary equation.
It happened for some degeneracy because we are going to zero, and sometimes things that are not supposed to be equal are equal in practically the same order, and that's why it mostly happened, and that is looking like the derivative with respect of. Okay, never. Yucks. In integrals it appears. So let's find the solution. x0, the zeroth order solution will be just 1. Next order, x solution, we will guess 1 plus x1 epsilon. By the way, if you're incorrect about the next term, x1 should depend on epsilon. If you got it right, what will actually happen, if you will do the correctly the next order asymptotical analysis, you will get that x1 is a constant. Why it's so nice to guess how something like that behave and what is the scale, because then you find the first one, the second one, and from that you can guess the nth one. I will actually, you know what, it's a good idea. I will give you in homework one that you will find the first one, second one, and if you can guess that the nth one from there, it's nice, and if not, you will work on it and find that. I will not ask you to prove that, and I will not decrease points on doing it wrong, guess it's wrong. I will decrease point only on the first order to find the first orders wrong. It actually will be a nice one, and it's not taking too long. So let's continue. So we have here epsilon 1 plus n x1 epsilon plus 1 plus epsilon x1 equal to 1. So what we get here is that vanished because we have epsilon times that is only contribute for second order, the next order, and we find that thing, that and that is vanishing, and then we find that we have equation epsilon plus epsilon x1 equal to 0, therefore x1 equal to minus 1. Here we go, we find the solution, and doing next term, how it will look like, we will have to guess x solution for converge one. It will be 1 minus epsilon plus x2 epsilon squared, and then guess a solution. Guess what? It's not the it's not bad. Will be just doing it. You will have to be careful because you have another thing that gets a lot of students to...
יש פה הרצאה?
כן, יש פה תרגול. That fails, that a lot of students miss. That will be the next order contributes something, and sometimes even the third order can contribute something, so you need to be aware of that. So Let's try the next order. How do you say ADHD is קשב וריכוז?
Yes, ADHD.
Yeah. Yeah, my ADHD kill me because every time they interrupt or is moving here. When I just arrived to the university, if someone will interrupt like that and he's not related to the tutorial, you just scream on him, go away like a teacher in school. Okay. Epsilon. Now the first order will be 1 minus n to the what? Epsilon plus x2 epsilon squared. And next order we can neglect that and only take that to the next order.
Should be minus.
Yeah,
And that
minus,
will be
Minus
x2 or
inside.
minus, yeah.
minus inside, yeah. And now the next order will be something like that, that is coming from the binomial expansion, that is n choose 2. And here we have epsilon squared, and that's looking fine, because now finding a solution is not very hard. x2 epsilon squared equal to 1. I just want to present here that binomial expansion, you have to remember that. In that stage in your academic career, if you want to do that very quick without having mistake, remember the multiple expansion of binomials. Okay, I mean 1 plus a1 a k to the nth power, and then you want to find the general literal, it's called, or it's a multiplication of all of those, that this combination will, what will be the coefficient.
Why did you took two terms in the Taylor expansion?
Because before I took the first, I took first order to epsilon, and now I'm taking the second order. So I'm keeping everything to epsilon squared.
Ah, okay.
That's it. So we just, and luckily here n is integer, but sometimes n is not integer, and that is a pain, because I think there is generalized with gamma function and all of those stuff, but I will be honest with you, if I will get something and I will say, okay, I need to develop that to fourth order, I'll just Taylor expand it very quick with derivatives and find the derivative around 1 or something like that, and do it. But there is generalization of something like that to expansion with gamma function and a lot of those stuff. I'm not willing to do that. For me, it's just technical how to find epsilon squared. Oh, you probably wonder why I took that, because times epsilon it's negligible. Yeah, I will drop that. Why I took it here? You can say that before and prevent that. You can totally do that, but I just took that to show you. Hey, look, that will appear, and that is how you do that.
Look, I know binomial expansion.
Yeah. No, you need to know that, because sometimes you have tests that you need to find seven orders, and it's just technical, and if you're doing something wrong or not doing it exactly like how you should do, understand what I'm trying to say. You need to know all of those quick tricks that will give you a nice result at the end. Okay, for me it's just technical to find x2. I will continue to our point of the tutorial. The nicest part is the physical problem, in my opinion. Oh, actually I didn't. Okay, let's solve the divergent, because we find only one solution. But we are actually expecting that to happen because epsilon equal to 0 gives us a first order polynomial. how do we find the next order? Or we'll find the width, and from there it's practically the same to find the divergent solution. And I'm pretty sure it's written nicely in my tutorial notes, but it's very easy. If you want, I can continue to find more terms, but let's do the hard part of that question. T divided by delta, and now we will want to find what is the width of the equation. So let's write here epsilon divided to the
n t to the n.
I don't know who said that, but
It is.
okay. So what we will do, actually, this time I can't run from just multiplying by delta. Why? Because I don't like that here we don't have the epsilon that we had last time, that regularized that term. So we want everything to converge, every coefficient, even from that. But for that it's already nice, converging for the 0th order term, right? It's delta to the 0 power. Here we can regularize it with setting some balance between epsilon and delta, but here there is nothing to set in balance. Okay, if you want to set delta to be 1, but what you did if you set delta to be 1. So what we're doing is multiplying by delta. Now it's delta to the n minus 1, t to the n plus t equal to delta. And now what you will do is find that delta, you want it, delta to the n minus 1 power will be the same order of epsilon, so delta is epsilon to the n minus 1 over n minus 1 power. Why I said that? Not formally, but I said that to be 1, equal, and solve for delta. That's it.
Just multiply both parts by delta, right? And then
I multiply here
Okay.
by delta for the equation and set it, and here I found the first leading term, and that is actually also, in that case, it's also the scale, because now the equation looks like t to the n plus t equal to delta. From that you can infer that the solution will be something that looks like an delta to the n, because now no coefficient of that is looking like that, and from here it's just the same stuff of doing perturbation theory, and it's practically the same. You have something? Look like you have a question. From that we got the insight of the problem, and now it's easy, right? Now it's just technical, taking each time the next term. It's practically what we did in Pade, and we just find the width, that in this case is also the scaling of our system. Usually it's like that. I were wise enough to bring you the first example that it's not like that, so now it's not looking intuitive to you that delta is also the scaling of the system. Okay. Is it clear? Can I continue to the physical problem? So, I hope you understand why it's so nice to know the scaling of the problem, and why it's so good to have the width of the problem. You see, that is just, now you get something that is very intuitive to solve, and you have a better understanding of problem that looks like that than problem that is, where is that? I wrote it here. Here. that looks like that, because I have epsilon in the highest order term, and I don't have any intuition on that. How x, the solution, will behave. But from finding the leading term, now I have an intuition. Okay? It's practically the solution of just saying that is leading order, epsilon here, and then solve that, but I'm not sure that is exactly the same. Because here you will get 1 over, you will get n solution. Okay. I will have to check that, but I think it's equivalent. It's supposed to be equivalent. For me, it's the nicest way to find the perturbation and all of those stuff. To order of 1 of miscalculated stuff that apparently can happen, that is the point of I'm trying to teach you. Don't think I have mistakes, I'm just mistake in what I'm presenting right now, but I'm not sure, because saying that epsilon next to the n is the leading order, you actually get something that is the leading order will be something in order of 1 over epsilon to the 1n, right? Something that in order of epsilon to the minus 1 over n. And we got delta that is behaving differently. Our leading order were 1 over n minus 1. They are practically close to be the same, but I'm not sure what happened here. If you asked what happened here and what is the fix for that, I can look on it and give you answer for that. But tell me if you want that. I think it's just something with dominant balance, because I did here something that's a little bit different. Yes. Yeah, I know what is the problem. You can't say that is dominant. Actually, what you said, that sometimes 1 can be negligible, right? You throw away 1. Because 1 is negligible compared to x that diverge, and x diverge, because you are dealing with diverge problem. You don't have, like last time, that epsilon that will regularize what happened here, right?
In the case of here, you
can see so actually you throw 1,
and then
that's what I said, that sometimes, yes, you're absolutely right. That's why I told you are absolutely right, and that were a good anecdote. Sometimes you're throwing the 1, and then you're left with n minus 1 order. But when you're doing things like that, I didn't even think what to throw, I just took, balanced, then I got the solution. Here I had to think what is the negligible part. Okay, sure, it's very intuitive that 1 will be the one that goes, because you're trying to find a divergent solution. X to the n, for like what Dima started to say in the start of that problem, for n goes to infinity, we expect that to be infinite for the divergent solution. So it can be negligible for the divergent solution, and x can be negligible, and 1 is the only one that will be constant for the whole solution. So those terms have to balance each other. That is what actually happened here, but you agree with me that is much easier to do dominant balance like that? I think it's much easier. I don't think it's written in Bender's book, and I think I once showed that to Kessler, and he told me that is a nice way of doing that, because I did something that you will study, I think, only next week, is boundary layers, and when you're trying to solve in boundary layers something, you're doing a similar method to that, and I implement that in perturbation theory. Okay, so So, okay.
Sorry.
I will wait because I were about to explain the system. Okay, go.
I will do it fast.
So, it's only me and you.
Oh.
If you have questions, that is actually a nice time. I convince you that doing it like that, you prevent mistakes.
I don't get the idea about width of the problem. So,
Whoa. You don't get the idea.
yeah.
Okay. That is
Because
general.
some,
That is general.
physical meanings of that.
Yes,
or
that how you catch the zeroth order behavior of that solution. You practically if you're trying to solve for x, okay, your width is delta, t0 is the zeroth order solution. That will bring you the zeroth order solution, right? And in that way you can find the zeroth order solution. And sometimes it's much clearer when delta is something like ln delta. So how do you find that thing? And now here it is a whole perturbation series. You understand what I'm trying to say? If you want to try to find something to its first order approximation. The width is just something that, if you want to think about that, that can be a characteristic scale of your system. Okay? That is how you find some sort of characteristic scale. That probably and mostly like what happened here will give you a nicer solution and nicer equation, because that is much nicer equation than that equation. I think you agree with me. Right, you understand why it's so nice, because here it's much easier to implement perturbation theory. Here it will be awful. You had to understand that you need to throw the one away, right? But okay, I can do that, sure. But you don't have to think about anything when you're doing it with the width. Okay, so let's show our system. It's practically, I will name drop something and then we'll say it simply. We're doing some oscillating plasma that will the whole name dropping, and practically what we will do is solving for electron that has some effect from ions distribution. Ions, particles with positive charge, electron generally particles with negative charge, unless, okay, electrons, and I were specific, in one dimension. So one thing that you can do is solve that. We assume there is only electric field, because if we want to look on electrons, the electric field and the electric field that comes, and we want to look on something like laser or something like that, you can look in a lot of plasma books on lasers. You will see the equation is look like that. You will throw away the magnetic field in this case. I know you're doing plasma physics, and therefore we always throw away the electric field.
Yeah.
But in plasma oscillations, in lasers and all of those stuff, you actually left with only the electric field. And what we will do, sometimes you have electric field that is almost constant, or something like goes like linearly, because constant is not very interesting. So he said, okay, it's growing like in laser, it can be in order something that goes like a polynomial to nth power of x with place. you move to something that it's decay or something like that.
But
So
from which order the polynomial?
what?
By which order the polynomial goes?
I wrote here n for general.
General.
To be general, but I will be more specific because now I just want to find that here. For the first order, what you actually get, because of the minus and a lot of stuff that involve plasma physics, you actually get x 2 dots equal to minus omega p plasma frequency, that in this case, only in this case, it is something that looks like e squared and 0 divided by m e epsilon 0. Okay, that is actual the value of the parameter. N is just density of particles that we assume that is all close to be constant. And what we are practically do, that is oscillator. But what we will do is just generalize it and write x squared plus omega p squared x plus alpha x squared. Because generally it can go with the place you are squared in some terms that here we set the amplitude to be constant, but it doesn't have, the amplitude doesn't have to be constant. It can also vary with the place it is, right? So that's what I just said here. That is actually saying the amplitude has some effect. So it can't be linear equation, because in linear equation the amplitude doesn't matter. So we have to expand it to that form. Alpha is just a coefficient that determined by the second order derivative of the electric field. Okay. It's just property that practically you will call it alpha and then find it with some sort of experiment. But you know my lab, we are not doing experiment and we are not very good with it. But we are good with analytical solution and math. So what we will do here, in the case that you get a physical system, you have to find small variable of that system. You have to do that. First step, second step. Something that you have to do in all physical problems. What will be our small term? Alpha. But small compared to what? We are in physics now.
To
We are
the
not
square root of omega.
units. That is a problem. So that is the case that is appearing a lot in physics, especially I know in astrophysics. In my research, for example, it's appearing a lot. That you have to add another coefficients of your choice, just constant, to add it to the equation to be able to compare alpha with omega squared, because that is what matters. And that have to be in units of length, right? To compare that. And what I will say, because I think it's nice, it's the largest length that I can get in the system, in the oscillation, that will be the zeroth order amplitude, A. That is a nice, it's practically L max, the largest length of the system. That is usually what it takes, and here it's the same as taking the amplitude. Okay? So our boundary condition will be something that goes like y of 0 is equal to 1. That is very nice boundary conditions. Okay? 1 units of A. Okay. So that is actually what I will do. and that is something that comes from experiment. And all of those stuff, you're looking on the zeroth order and you find the characteristic amplitude, characteristic scale of length, and then we can define epsilon of this system. Oh, let's do something before, and let's do something that I do it almost every time I'm dealing with new equation in physics. Rescale your system. So writing tau will be, we want things to be unitless, so tau will be omega p t, or yes, it's okay. Now tau is time scale, unitless time scale. And let's write x as a y. Y we already used to a function that doesn't have units in our course, so that will be nice. So the second order derivative, it will be d tau squared. Actually, we want t, so let's write t squared. It's actually omega p squared d squared d tau squared. Right? Everyone agree with me? And now just setting all of those stuff, nice stuff, and we find that omega p squared x, I will still denote that with 2 dots, but now it's 2 dots with respect to, let's call that proper time. Okay, it's a little bit cheating to say that is proper time, but intuitively it's practically, the intuition is the same, it's just time with the right units. In proper time it's units that depend on the velocity you are in. It's also some sort of scaling of the system. Velocity that in the scale of the speed of light, something that you've seen before but you didn't call it scale, and now I'm giving it a name. That is the only thing I did, is actually giving it a name. Now it will be y, here it will be y, and here it will be y squared equal to 0. And then it's very easy to spot what will be the small scale, because it just popped out of the equation, even for non-linear equation. So it is very easy to spot right now. Wait. Alpha and omega p squared, y squared equal to 0. Now it's very easy to spot what will be negligible. We want that to be very small. It's like saying alpha times a less much smaller than omega p squared. That is the actual physical condition. Why? We did some scaling of a that I choose to be the amplitude to get nicer boundary conditions. Why? Because I can. It's usually something that is normalized. You're choosing something that will normalize your solution. Why? Because it's nicer. I don't have much intuition on that. That is just something that will simplify, unless you have some physical quantity that pops out, so you will want it to be in your solution. For example, speed of light is constant of nature. H bar is also constant of nature, that you can play with it. Dima, don't put G and H bar in the same equation. That is very funny. I can tell about homework 3. You were amazing. I'm telling. No, I'm not telling. Ask Dima afterwards what he did in homework 3. That were
Gee,
amazing.
like
I really liked that.
G like the constant of
I really liked that.
gravity.
Dima, you're amazing. If I were able to give you more than 100 marks, I will for sure give you more than 100 marks. If I will continue like that, you will not put more jokes in the homeworks. I like jokes, so put jokes. So we will denote that by epsilon. And actually, who remember first year ODE course? That is actually analytically solvable. Actually, for each term I will take extra. It will be analytically solvable and with nasty equation that you can actually do perturbation theory on it. And in theory, it's just denoting u equal to y dot and do all of the substitution. And now you have a function u that is actually function of y you set it because you don't have x in your, I'm sorry, t time dependency. And it's usually appears a lot, but for what we need to do, we will do perturbation theory. We don't have to find general expression, but if you want to find general order perturbation, doing it with perturbation theory after finding the integral and all of those stuff are much nicer, but only by the end of the course you will study how to do right integrals. You can already do that from intuition, and because you're a physicist, so you're strong and you can do everything, but now we will do that with perturbation theory. So let's do that. What will be the zeroth order? Just epsilon is 0. So what will be y0?
Minus cosinus.
Yes, let's say cosinus tau. Why? Because I chose that. Remember, dot is tau, our proper time. And now the next order, y0 equal y solution equal to y0 plus epsilon y1. Why epsilon and not epsilon to the half? Because I want and I have experience and I can look, hey, that looks that it will do great. And actually, what will be more red alarm, more scary? Seeing epsilon in front of higher power of y or second order derivative?
With epsilon.
Yeah, with epsilon. Second order derivative, right? It will be much scarier because then you will have a lot of things like that can appear that looks like e to the minus t divided by epsilon, and then when epsilon approaches 0, it's exponentially approaching to 0, but like I told you, that is when you need to verify if it's approaching from right or left, because it depending if it's exploding or diverging, then you have two different behaviors that totally chaos. You will next lecture with Snarb you will probably encounter things like that. For now, that's why I told you we will keep it simple. Simple as possible. It's really simple, but you really have to know what you're doing and picking the right method. Right now I'm telling you, okay, let's do perturbation theory and all the problems are perturbation theory, but in practice you will have to find that yourself. Actually in test, שנרב also telling you what to do, so you can have a relief. In our test, Kessler told us, do whatever you think. Have fun. I can solve the test in 15 minutes. That's the only thing he told us. It's very funny. So the first order equation, actually the zeroth order solution of y from those terms vanish. So we have only epsilon y1 to 2 times y1. From here, the first order solution will vanish, so we are left with epsilon y0 that. And now, 2 epsilon here. Now just writing it nicely, y1 equal to minus half of 1 plus cosine of 2 tau. You already know I use some identity of trigonometry.
There is no double dot on the second one, y1.
Yeah, sure. You know how to find the homogeneous solution, and you know how to find the inhomogeneous solution by method of guessing what I did, or by method of variation, what we did in the start of the course.
Yep.
Instead, if you know the homogeneous solution, you know the non-homogeneous solution.
Here to do the variation, I have to use also sinus, right? I need two solution variation parameter.
I'm so wise, so I just guess the cosinus and then find two solutions, so I have the full solution.
No, I mean, if I have a second order differential equation,
You need to find two solutions
I have
that are
to use two
independent.
solutions. Yeah.
If I find a solution that has two, here I will guess constant and cosinus of 2 tau times some amplitude.
Okay.
I find two independent solutions, I won. I don't find that, I have to recheck what I did. But for my case, it were enough. Okay. Okay, if you really want to punch that question in the that equation in the face, do Fourier transform. That will kill it in a second. I promise you. You will get from that delta function, from that you will get delta function, and from here you will get some numbers, right? Yeah, because they're conjugated. Okay, exactly. And then you will find the solution and back transform. Fourier transform is really powerful trick. Remember that. I'm not sure if Snarb remember that, and that can simplify a lot of questions from Snarb's test. Remember Fourier transformation, and sometimes even Laplace transformation can be nice for different cases, because how derivative change is different from one to one. And sometimes Laplace is easier, but you can always implement Fourier transformation, and Fourier transform is exactly what Laplace do, but for imaginary k. So let's solve that. We already know how it's going like, so I will give you the solution. The homogeneous one, okay, we can just put that in the y0 solution. The coefficient can eat that and all of those stuff, because it's also an harmonic oscillator with the same frequency, right? So you can just eat that, and that's why the homogeneous solution doesn't matter. And if you want, you can, if you also include the homogeneous solution, you have to redo the boundary condition that we already did, and therefore you find something that is not, you have more constant than what you should have, right? So you need to balance that somehow. And now y1, just the inhomogeneous. I think that, Dima, tell me if I'm correct. I think that is what's written in my tutorial. And when I talk too much, I verify by calculating in my head. Yes. Okay, so very good. Don't ask me why you remember that and were able to calculate that in the head.
This is one solution. What is the second solution?
That is the non-homogeneous solution. You have only one.
Oh,
That's what I just explained.
I thought you said the homogeneous.
Okay, so we say that the homogeneous solution, there is no we don't need to talk about the homogeneous solution because it's just harmonic oscillator, and you can eat that in the zeroth order equation because it's the same equation. So what we have here, very simple, and now we can practically plug it in and find a general solution of how amplitude is changing with the, I will call that, with the solution. How the amplitude is changing. Actually, the most interesting stuff here is if you will, okay, we'll write the full solution, and then I will say some nice stuff about it, and then we will go home. Already over time. We will not pay attention to time. You are nice and quiet.
You're not continuing to a second perturbation?
You can do that. I say there is no point of it. It actually, the second perturbation will give you the whole point of that physical system because it will give you perturbation on the frequency. That is very interesting. Give you the perturbation if you will write omega of the system, the frequency of the system. Actually, the second perturbation, what it really gives you is perturbation on the frequency. That is very interesting. But I said, okay, that is very interesting, but we will not have time and I want to cover things really deep. But you can try to do that and you will find that you will have some shift in the frequency. And remember, here you have epsilon. Epsilon is not something that you don't know. And what you will find that the amplitude is actually depends on the maximal amplitude, right? Is because that is not linear equation, it has effect on the frequency. That is something that you never seen in undergrad studies. Okay, you've seen that in you too see that because you are still undergrad, but okay, that is something that is crazy. That means if you're oscillating like that, that omega will have really big effect, and if you start to oscillate something like that, it has less effect. How do you find that A, let's say characteristic A, it's just delta x, right? Taking x squared minus x squared. Yes, right? That is should be squared, and that is how you find characteristic amplitude. By the way, the averages will depend on A also. That will be set that to be A squared, but those stuff will also depend on A squared. Because and the frequency, the integral will also depend on A squared. Why? Because you're integrating on something that looks like omega p plus epsilon delta omega. So you will get equation and you can extract the characteristic length. It's called the moments method of, you maybe heard that from statistics and probability. That's called the moment method in general. So let's finish by writing y. Solution of y is just, okay, let's write that x solution because it's just multiplying by a. That is just a cosinus tau plus, let's say, minus a half a epsilon plus a divided by 6 epsilon cosine of 2 tau. And that is practically the solution, and the most interesting part of it that the amplitude what you will see is actually, if you will integrate on tau of actually doing it on tau it will not depend on A. That is a little bit the trick that you're doing, because now tau is, you did it with omega p, but it's already second order correction to do it, so that's why it's right, and you want to find first order, zeroth order solution to A. Don't want it to depend on epsilon. And then you find that A divided by 2 epsilon is the solution. So that's where it's practically very interesting, because that is something that you can see with your eyes. Okay, if epsilon is big enough. For me, it's very interesting if you ask
So
me.
there is a variation in the...
You want to find the variation? Just do integral on that and you will find that. Trust me.
תודה רבה.
אני יודע מה.
Thanks.
נחמד, נכון?
ממש.
זה פתרנו פה משוואות לא ליניאריות בקירוב, מצאנו זה. אתה אשכרה, אתה מרגיש את הפיזיקה בדברים האלה. זה כאילו...
במעבדה כללית מראים שבמטוטלת, הכי פשוט בעולם.
כן, אני חשבתי לעשות
יש קשר בין
מטוטלת.
זמן המחזור לאמפליטוד.
כן,
במעבדה
אני...
כללית כאילו היא נועה.
זהו, אני חשבתי על לעשות אגב מטוטלת, אבל אמרתי, אני יכול להנפיץ פלזמה.
למה לעבוד עם מטוטלת שיש חומרים מגניבים יותר?